other lecturers are telling you are conceptually wrong. I hope that by the end of my lectures there are certain words like string vacuum that none of you will ever say again in your lives. So we'll see how far we get with that. No. I also think that a lot of the work that people who work on string vacua are doing will survive a lot of what I'm saying to you. But I think there are important conceptual issues here. And as you'll see, it leads in particular to a very, very different picture of what it means to live in de Sitter space, as we apparently do, and what the quantum theory of a de Sitter space is, rather different than the landscape picture, which is the conventional picture in string theory. So let me start by talking about the effective potential. In quantum field theory, an effective potential is a function. And by the way, let me emphasize there are actually two uses of the word quantum effective potential in quantum field theory. There's the 1pi effective potential and the effective low energy potential in the effective low energy action. I don't think anyone in string theory pretends that there's anything like the former. So we're always talking about an effective low energy action in the sense of Wilson. We have lots of evidence that things like that exist in string theory, but there's something we do with them that I think is not correct in string theory. So in quantum field theory, the effective potential determines different stable and metastable translation invariant states of the same quantum Hamiltonian. The quantum Hamiltonian is defined by a conformal field theory and a relevant perturbation of that conformal field theory. The different states are different translation invariant states. They differ only in the infrared. They have very similar properties in the ultraviolet, in fact, exactly identical properties in the ultraviolet. And there are various things you can do in them. So, for example, if you're in a state characterized by a field expectation value phi 2, you can make an arbitrarily large region of space which is in the phi 1 vacuum. So you have phi 2 every place outside, phi 1 in here, and that radius r can be as big as you want. And you can do that starting essentially with scattering states. You can throw stuff in from infinity, a finite amount of energy. You create this metastable region of phi 1 vacuum, and it lives for a certain amount of time, and you can go into it and explore what's going on inside of it. So even if you live in the phi 2 vacuum, if you had enough energy available, you could do a scattering experiment and find the phi 1 vacuum.
Can we turn some light?
Turn off?
The light makes it hard to see the overhead.
Okay, the problem is at a certain point. Okay, which one should I? Yeah, why don't you do that for me? At a certain point, I'm going to start using the blackboard, and so we're going to need both of them at the same time. So, okay. This picture is a space. This is a region in space at a fixed time when I've created this region of phi 1.
Sorry, so Tom, you're thinking phi 2 is somehow like the true vacuum?
This is a case for the moment. Think about two exactly stable vacua.
Okay.
Or one unstable, one stable, and I don't tell you which is which.
And I'm just making sure you're not making a statement about infinite versus finite volume.
I'm only talking.
So, for example, the energy splitting between the two states with the finite potential energy difference is infinite if the volume is infinite.
That's true, but if this is a finite region, this is a finite energy.
Yeah, but the Hilbert space where you have phi 1 outside is a different Hilbert space in infinite volume.
I agree with that.
Yeah, okay.
That's all that I'm saying is that you have the Hilbert space with phi 2 outside. You can create a state in an arbitrarily large region R in which things look like they're in phi 1.
Yeah, sure.
That's all I'm saying. Another property, if we have an effective potential that looks like this, well, let me make it more dramatic. One state is obviously metastable and can tunnel into the other. When it tunnels in a very smooth way, and a bubble forms, and inside that bubble, you locally just approach the second vacuum state, everywhere inside the bubble in a smooth way. Next thing, if I do scattering experiments in the Hilbert space characterized by phi 2 everywhere outside, or phi 1 everywhere outside, and I choose all the kinematic invariants large energy, large momentum transfer, then those experiments have exactly the same result in the two different vacua. Even if the particle spectrum in the two different vacua are different, when you go up to very high energies, those differences don't matter. The scattering amplitudes are the same. Finally, if I look at the density of states in a finite volume at very high energy, again, there is a finite energy, an energy density barrier sort of given by this height, and above that, the density of states in the two different vacua looks exactly the same. Every single one of these characteristics of field theory vacua fail in any theory of gravity, and you can see that just by doing gravitational effective field theory. So let me talk about the first simple thing, this idea of creating a region where you're in vacuum phi 1 inside of vacuum phi 2. The culprit and the hero of all of what I'm going to say is the black hole. And what I'm going to be leading you to is a picture in which the intrinsic feature, the fundamentally new feature of any quantum theory of gravity, has to do with the nature of black holes. And I will, in my last two lectures, I'll talk in detail about how that leads you to construct a more flexible theory of quantum gravity than the current ones we have in ordinary string theory. Ordinary string theories, I believe, will turn out to be special cases of what I'm going to tell you about in the last two lectures. So here's a simple calculation. It's up there on that last line. If I take a region of radius r and I construct by throwing stuff in from infinity this region where phi 1 is where phi is equal to phi 1 in radius r, then the mass that's enclosed in that region, the amount of energy, is r cubed times delta v, where delta v is the difference in the energies between those two minima, plus a tension times r squared, where the tension has to do with the following. There's some transition region in this configuration. Imagine doing this by throwing in a classical field configuration from infinity. That'll create a static, instantaneously static configuration, which will have an energy that's bounded from below by the energy of that static field configuration. And that energy is that energy has a piece in it that has to do with the gradient terms of the field, grad phi squared, going between those two vacua on the interface between the two. I've drawn that interface here as a sharp thing. And if all of the energy differences are finite, if there's not only the difference between here and here, but the difference between here and here, if those are all some finite number, that tension in that wall will always be finite. Well, you can look at this formula. That formula is written in Planck units. And in Planck units, at some point, that mass becomes bigger than r. But r, in Planck units, is the Schwarzschild radius of a black hole of that mass. So what you find is that any time you make such a field configuration, if R is big enough, you've in fact, instead of creating what you thought you created a black hole. This scaling that I've written down here is appropriate for d equals 4. This is true in every dimension of space-time for which there are black holes. In asymptotically flat space, that means d greater than or equal to 4. Yeah.
Just to make sure that I'm understanding it right, this background that you're talking about, I mean, I could think of it as a spherical solution.
Yeah, yeah. I'm thinking of it as an instantaneous snapshot. It doesn't have to be a stable static solution. I've thrown in stuff from infinity. There's some kinetic energy, phi dot squared energy 2, which I haven't taken into account here, but that's a positive addition to this. It's enough to have just the static energy of the instantaneous configuration to show you that at a certain radius r, I will inevitably find that the Schwarzschild radius, which goes like m, is bigger than the radius, just because of the scaling of these formulas. The bubble is always, of course, at a higher energy. I'm talking about, for the moment, I'm talking about a bubble. I'm in some vacuum state, and I'm creating a bubble at a higher or equal energy. Okay? Equal means that there's a positive contribution that scales like r squared, even if delta v is 0. And since it scales like r squared, it beats out the r. Larger than r in Planck units, right? So the equation doesn't look dimensionally correct every time you see a dimensionally incorrect equation in my lectures. The thing that's missing is powers of the Planck scale. Okay, and I'll occasionally have them in there, and occasionally I'll not have them in there. So the Schwarzschild radius of a mass m in 4 dimensions grows like m. Okay? That's what the metric looks like. And we get the 0 in the metric, right? This is ds squared equals minus that times dt squared plus other stuff. And the Schwarzschild radius is the position of that singularity, and it grows like m. Okay. Now, in the de Sitter case, so let's assume this was, say, Minkowski space, so that this was an asymptotically flat situation, and we were trying to create a de Sitter space. And what you see is that because of the tension term, you create the black hole parametrically before the amount of energy in that region due to the delta V becomes of order 1. So that's the criterion that you need. R has to be large enough so that this thing is of order R in Planck units in order to see de Sitter space being de Sitter space. De Sitter space doesn't look like it expands if you look at it over distances smaller than the Hubble radius. The Hubble radius is defined by the equality R cubed delta V equals R. And so this says that the black hole forms before you get to see de Sitter space over its Hubble radius. This situation would correspond to something that Lee and Wick, many, many years before any of you were born, called abnormal nuclear states. You can have resonances like this in ordinary quantum field theory, but you can't have them over very, very large regions, arbitrarily large, no matter how small V is. V could be very small in Planck units. Eventually, as the radius gets large enough, this will happen, and you won't be able to construct this vacuum, and you'll never be able to see it behaving like de Sitter space if, indeed, it looked like de Sitter space. So there is a de Sitter solution in the presence of gravity of these field equations where the field just sits in this false minimum with positive energy density. And the observer observing here can never see that region at all behaving like de Sitter space. So the de Sitter so-called vacuum doesn't manifest itself in the four-dimensional theory. Very unlike what happens in quantum field theory. Okay. There are very similar conclusions if I take this lower state to be an anti-de Sitter space. Yeah.
Does this hold if the zero is all the way out at infinity in field space?
That corresponds to a situation where you don't really have a stable Minkowski vacuum, so it's more complicated to think about. The scaling remains the same. But I prefer to think about situations where it appears to you that you've got a stable situation down here. We know what we're talking about in some cases in string theory when we have zero or negative cosmological constant. Okay. So in low energy effective field theory, including gravity, a metastable minimum doesn't allow you to construct the other vacuum and see it behaving as it's supposed to behave gravitationally. Now, very similarly, you can think about the large S, large T scattering amplitude. And this was something that was first thought about by Roger Penrose for head-on scattering, and then it was considered by a lot of other people in general relativity. There's a lot of technical GR that goes into it, but roughly speaking, what's going on is the following. If I think about two particles that are scattering, and the impact parameter here is less than the Schwarzschild energy, the Schwarzschild radius that corresponds to the center of mass energy, okay? Then what happens if I look at the metric of this at the point the particles pass each other, thinking of these as just classically moving particles interacting with the gravitational field, at the point that they pass each other, if I take an instantaneous snapshot, there is a Schwarzschild field very far away which captures the total mass of this system, which is the center of mass energy. So that Schwarzschild field has a Schwarzschild radius. If the impact parameter is smaller than that Schwarzschild radius, the particles have fallen inside the black hole. All right? And these are just words. This is a picture. There are rigorous calculations in general relativity that show you that in these circumstances, you always form a space-like singularity using the Hawking-Penrose singularity theorems. And if you believe the cosmic censorship conjecture that every such singularity eventually evolves into a black hole, that is, that it's shielded from the external observer, then you know that actually a black hole forms here. Now, yeah.
So let me just check. So let's just consider only moduli space. So the meaning of moduli space, only purely supersymmetric compactifications. Would you say that it's sensible to say that different points in moduli space somehow are in the same theory? And that,
no.
Because you could make the same argument. You have some domain walls surrounding.
Yes. So the answer is no.
Okay.
What you actually, if you go back to the previous argument, what happens is if you try to move more than a Planck distance in field space, okay, in moduli space, where I'm measuring fields in units of mass. If you try to move more than a Planck mass, even though there's no potential on the space at all, you still run into the same problem that you create a black hole. Okay? Similarly with the large S, large T scattering. Now, scattering produces black holes. We're not finished with the argument yet because maybe the decay of the black holes is the same in all of these different points in the field space. Maybe this point and that point have the same black hole decay probabilities. The answer we know is not, because Hawking told us for large black holes how black holes decay. Black holes decay thermally with a temperature that depends on their mass. And as I lower the mass in asymptotically flat space, that temperature goes up. And so if I watch the black hole decaying, I start to see the spectrum of the theory. And of course, the characteristic, even in field theory, of different points on a different stable minima or metastable minima on an effective potential, or different moduli in a supersymmetric theory which has a moduli space of fields. One of the points is that generically the spectrum of the theory changes as you move from one point to another. And so the black hole decay will be different in different vacua. Let me use that word, but I'll stop as soon as I can. And therefore, they're not vacua. All right? They don't have the property that field theory had, that the high energy scattering is the same independently of which point on the effective potential you're living at. Finally, let's talk about the high energy density of states. So here, I have to make what is, in many cases, a conjecture, but in ADS-CFT, it's a rigorous theorem, which is that the high energy density of states in theories of gravity is dominated by black holes. Why do I say that more generally, aside from the fact that it's rigorously true in ADS-CFT? The reason is that if I start to think about packing energy into a finite region of space-time, then, of space, then what happens, as we know, is that I can start putting more and more stuff in. And if it's described by field theory, I know what the density of states is going to behave like. And in a calculation that I'll be reminding you of later if you've never done it, what you find is that at a certain point, you put in enough mass that a black hole forms. And at that point, you find that the entropy of the black hole, which I want to interpret as the logarithm of the number of quantum states that corresponds to that field configuration, that entropy is much bigger than the field theoretic entropy that you had before the black hole formed. And so the black holes seem to be the best way to get states for a given amount of energy. And so they should dominate the high energy density of states. Well, if you look at the formula for black holes, the way it looks is the following. In d dimensions, the Schwarzschild metric looks like this. I'm going to give you a homework problem. In which you derive this formula, once I get it right. And in this formula, we're now in d space-time dimensions. This is the Coulomb potential in d space-time dimensions, or the Newton potential, more properly. That has a d-dependent coefficient in front of it. Part of your homework assignment is to calculate that. It doesn't matter at all for what I'm saying. This corresponds to putting in a cosmological constant, which has a radius, gives a radius of curvature to space-time r. And the minus sign corresponds to de Sitter space. The plus sign corresponds to anti-de Sitter space. And this formula now allows you to calculate the black hole entropy very simply as a function of the mass. So you just look for the 0, and then find where in little r the 0 is, and raise it to the d minus 2 power. Here's what those formulas behave like if I look at black holes of very large mass, such that the Schwarzschild radius is of order or bigger than the anti-de Sitter radius in anti-de Sitter space. And I'll talk to you in a minute about what happens in de Sitter space, which is really kind of weird. In anti-de Sitter space, you get this scaling over here. Okay? So you get a scaling which should already suggest to you ADS-CFT. This is the scaling you would expect for a conformal field theory in one less dimension of space-time. And furthermore, the coefficient in front of that depends explicitly on the anti-de Sitter radius. And so the density of states, the coefficient, this tells you, or hints to you, that there is a dual theory to anti-de Sitter space, which is a conformal field theory. A conformal field theory has an energy density that scales like e to the d minus 2 over d minus 1, where d minus 1 is the dimension in which the conformal field, the space-time dimension in which the conformal field theory lives. And then the coefficient in front of that, roughly speaking, counts the number of fields or the number of degrees of freedom in that conformal field theory. We see here that the high energy density of states in any theory of gravity is behaving in a way that depends explicitly on the value of the cosmological constant. And so if you had an effective potential that looked like this, with the zero of energy up here, and I had two different ADS minima in there, you said, oh, those are just two different vacuum states of the same quantum system, you would find that this one had a very different high energy density of states than this one. Okay? This is something that's obvious to anybody who studied ADS-CFT. In ADS5 cross S5, for example, the value of the cosmological constant in Planck units measures precisely the n of SUN super Yang-Mills theory. All right? So these are not different states of the same theory, but rather different Hamiltonians, different models. In Minkowski space, just 1 second, it's even worse. In Minkowski space, the scaling is completely different, and I'll let you notice that the exponent is greater than 1. This is the oft-quoted statement that black holes in Minkowski space have negative specific heat. Little homework exercise in thermodynamics, go home and show to yourself, or it's really in statistical mechanics, that if the density of states, the log of the density of states grows faster than the exponential of the energy, that precisely corresponds to negative specific heat. So the form of the scaling relation is completely different for black holes in ADS and in Minkowski space. And now Joe had something to ask.
We have this idea that in gravity, high energy is no longer fundamental because things get bigger past a certain point. And so why is the high energy edge of the spectrum a measure of things being the same theory?
I don't think that high energy is not fundamental, number one. Number two, I'm criticizing your use of an effective potential which was based on this idea. The whole idea of vacuum state in quantum field theory means I've got this theory that's defined by a relevant perturbation of a CFT. That's the high energy definition. And then there are different infrared realizations of that same algebra of operators, that same Hamiltonian. There are two different Hilbert spaces that differ only in the infrared. I'm telling you, in a theory of gravity, that idea just doesn't work. You also go around, I'm sorry to put it all on you, but calculating an effective potential by doing low energy effective field theory. But when you go to a different point on the effective potential, you dramatically change the high energy behavior of the theory. That, I think, is a signal that something is wrong. Okay.
Just to comment back on the entropy scaling, those are referring to large ADS black holes?
Those are large ADS black holes. We unfortunately don't have a good modeling of small ADS black holes in ADS-CFT, but we know the way they behave because we now know that Bekenstein and Hawking were right, and therefore their formula tells us how Minkowski space or small ADS black holes behave. Yeah, I mean, typically BPS states are special in this situation. They're not. This is not the typical behavior for BPS states. I'm not sure what the point of the comment was. What's definitely true is that the high energy behavior of a theory in general never has anything to do with BPS states. Okay? BPS states are always very special, low energy, almost vacuum configurations in a way. Okay. Now I'm going to come to what I consider one of the most important parts of my entire course of lectures. And it's really an update on a fabulous paper. I don't see the eraser anyplace. There it is. This is not the right eraser. Ah, okay. You've all, yes.
What do you consider the, so let's restrict the AES map too much. Consider the conformal field theory that you get by tensing together all the conformal field theory. Couldn't that theory, and first of all, that theory would describe as like,
That theory is sick from the ADS-CFT point of view.
well,
I mean,
disconnected copies of the universes that I could really want.
So it's not talking about a single ADS universe.
Well, does that matter if I can't probe the other ADS universes?
Well, if they're decoupled, they're decoupled.
Yeah, but then I can entangle them, right? I can consider entangled states. And so presumably I could build geometries maybe which probe both.
Yeah, but the way you entangle them is by coupling together two theories with
That's considered a mixed state, right?
a mixed state is a mixed state, right?
Yeah, but it can still have a class.
I can entangle together any two quantum systems that you like. All right? I'll entangle a spin-a-half particle spin with n equals 4 Yang-Mills theory, or a harmonic oscillator with n equals 4 Yang-Mills theory. What's the point?
Well, for example, the
I'm sorry for being aggressive, but this is a question that.
block gate geometry, right? You can think of it as a mixed state in a product CFT, two copies of it.
That's true. It's a very special mixed state, which is the one that you use in thermal field theory to calculate the partition function in one geometry.
So I'm just wondering if you could do a construction like that to actually have.
Well, I think that there are a lot of solutions of general relativity. I doubt that I'll have time to talk about this in these lectures, but I'm happy to talk privately to anybody who wants to listen. There are a lot of solutions of general relativity with bifurcate horizons, like the full Schwarzschild black hole. Those all correspond to mixed states, and some of them correspond to sensible mixed states in which have a use in a particular theory, and some of them correspond to silly things like entangling together a spin with n equals 4 Yang-Mills theory. And they appear as solutions of general relativity even with smooth initial conditions on a space-like slice. So it tells one of the things that that's very useful for. Is another point that I'm going to be making in these lectures is that in general relativity, boundary conditions make a lot more difference than they do in non-gravitational quantum field theories. And the precise meaning of what space of solutions of general relativity go into a particular quantum theory is a very, very delicate issue. And there are numerous places where this comes up. That's one of them. Okay. Now let's talk about tunneling, because this is one of the most, dramatic ways in which this picture of two minima on a potential somehow being connected with each other manifests itself. And the famous paper on this is Coleman and DeLucia. On Spires, they spell it with two C's, but I believe it's only one. This is one of the most fantastic papers in the whole history of our subject. If you haven't read it, read it very, very carefully. You'll also find one of the funniest quotations in the history of theoretical physics there as well. So that's a little bit of spice to get you to read it carefully. And the problem with the Coleman-DeLucia paper, but mostly with everybody who followed after it and quoted it without thinking about it too much, is that they give the impression that tunneling in the presence of gravity is a small perturbation on tunneling without the presence of gravity, as long as the energy densities involved are small compared to the Planck scale. One of my primary purposes here is to show you that that's just simply not true. Okay? Okay. So, first of all, and this is very explicit in Coleman-DeLucia, if this state is whatever you like, I don't care what its cosmological constant is, but this one is negative, people always use the phrase, another phrase that I hope none of you will ever use after hearing these lectures, tunneling to anti-de Sitter space. Ain't no such thing. It never happens. What instead happens, as I hope to be able to show you in a little bit, is that you tunnel into this region of field space initially, but then the classical evolution after tunneling does not nicely settle down to this point. And in fact, what happens is that the universe crunches. The bubble that you've created is a bubble. It expands outwards as far as an external observer is concerned at the speed of light. But internally, it crunches. It undergoes in what is typically a microscopic time scale, sort of the Hubble scale associated with this negative cosmological constant, which even if this was a small cosmological constant, there's no reason for this one to be. The Hubble scale, on the Hubble scale time scale, it crunches. And furthermore, when it crunches, as of course you would expect, everything gets excited. The field in particular doesn't stay in this region of field space. So imagining that you're tunneling to this point is just blatantly, in the classical solution itself, wrong. All right? So you never tunnel to anti-de Sitter space. Furthermore, a lovely paper by Horowitz and Hertog clarified what had until then been a very puzzling issue of what tunneling from anti-de Sitter space could mean in a theory where anti-de Sitter space is defined by ADS-CFT, by some conformal field theory. What does it mean for a conformal field theory to be unstable? Well, what Horowitz and Hertog showed is that if you pay attention to the boundary conditions on the instanton field, that the boundary conditions on the instanton correspond not to creating a state in the original conformal field theory, but to perturbing the original conformal field theory by an operator which is unbounded from below, making a new field theory which doesn't have any sense at all. And so the statement that is, I believe, the correct interpretation of the Horowitz and Hertog paper is that you never tunnel from anti-de Sitter space. You never tunnel to it, and you never tunnel from it. Okay? I hope I'll be able to show you some. That one I won't be able to show you. I'll just mention very quickly.
Well, there's something called Coleman-DeLucia bound, right?
Yes, exactly.
You cannot tunnel if
Exactly.
you have too much tension.
I'm about to talk about that. But I'm talking about cases. So there's the very interesting point in the Hertog-Horowitz paper was that they considered an instanton which, if it had been a real decay, would have been the decay of the supersymmetric ADS4 cross S7 solution. So it was totally crazy. And in fact, for the reason that you said, it wasn't really a tunneling, but they pointed out the solution exists. It's not that there's no instanton solution in that case. The solution exists, but it corresponds not to a state that can be created in this ADS vacuum, but rather to a perturbation of your theory of quantum gravity by an operator that's unbounded from below. Okay. Now, tunneling from flat space is really interesting, and this is the point that Miriam was about to make in a rather special case. And I should say that a lot of what's going on here, I first learned from Miriam and her work on domain walls. So here's the statement which is true about tunneling from flat space. And I'm going to say it to you in a way that should make it fairly obvious. So here is a lambda equals 0 minimum of the potential. Now, I want to tunnel from that into this negative region of potential. Can I do it or can't I? Well, there's a famous theorem in general relativity, which you have to prove Lagrangian by Lagrangian if you have general relativity coupled to other stuff. And it's called the positive energy theorem. The positive energy theorem tells you, without doing any further work, that if you have a Lagrangian for which it's true, there is no such tunneling. Why? What is an instanton? An instanton is a configuration which is localized in your asymptotically flat space. And I'm talking about the configuration to which the instanton tunnels. So as always with any kind of an instanton, you start out and you create a field configuration that moves over this barrier. And then there's a place where the motion becomes classical. And that's the so-called bubble solution. That's the beginning of the classical evolution after the tunneling. That bubble is a zero energy state by energy conservation. Okay? But if you have a positive energy theorem, the positive energy theorem that says any solution of the equations of motion that is not Minkowski space has positive energy. So there can't be any such bubble. And therefore, there can't be any tunneling. So now you can ask the following question about the space of potentials. Okay? And this, I hope I'll have enough time to give you some idea about why what I'm about to say is true. So we think about the space of all potentials, and it can depend on any number of fields you like. My pictures, of course, refer to a single field. And I have, in the space of potentials, I'm only looking at potentials for the moment that have such a zero energy minimum. Now you can ask, what do I have to do to decide whether there's a positive energy theorem or not? For which potentials is there a positive energy theorem? For which potentials isn't there a positive energy theorem? So very crudely, this argument can be made a lot better. There's sort of a parameter that you can tune, and if you tune it too much, you'll violate the positive energy theorem. And so it looks like, for example, here it would look like if I made this really, really deep, all right, it should be possible to get very, very negative energy states that were still asymptotically flat at infinity. And so it looks like if you tune one parameter, you can violate this theorem. And so the statement is, and this is a statement that can be established on a much more rigorous basis than that in the space of all potentials, which is, of course, an infinite dimensional space, there's a codimension 1 wall, which my collaborators and my collaborators were Anthony Aguirre and Matt Johnson. We called this wall in the space of potentials the Great Divide. If you're on one side of the Great Divide, there is no positive energy theorem. If you're on the other side of the Great Divide, there is a positive energy theorem, and there's no tunneling. What happens right on the Great Divide, and this is precisely what Miriam was referring to, there's a critical wall, and on that critical wall precisely, there is, for that particular class of potentials, there is a static domain wall solution that connects the ADS minimum to the zero energy minimum. So as most of you, I hope, know, if I take a domain wall, in ordinary field theory, it's just a domain wall. If I put it in a theory with gravity, it backreacts on the geometry. And the backreaction on the geometry is such as to make a difference in the cosmological constant on the two sides of the domain wall. Any of you who know Randall syndrome know this? Any of you who know about D8 branes in type 2A string theory know this? These are all examples of domain walls. Static domain walls like that are unusual. If I take a generic Lagrangian of scalar fields coupled to gravity, you won't find them. This, in fact, you know already without gravity. If I take gravity, a theory without gravity, and I have a situation like this, where there are two minima that are not degenerate with each other, then there's no static domain wall. One of them tunnels into the other. If I want there to be a static domain wall, I have to tune things so that the two minima are exactly degenerate. Sometimes I can enforce that by symmetry. In gravity, this is no longer the criterion, but the criterion always involves that tuning of one parameter. Okay? And if you look carefully near a Lagrangian that has a static domain wall, you can vary any one parameter in the potential and see that if you vary it on one side, you can make negative energy excitations. And if you vary it on the other side, you can't make negative energy excitations. And so this is the barrier in potential space between theories which have instantons where you decay not into anti-de Sitter space, but into this terrible big crunch that I told you about, and where you don't have such instantons. Yes. So it, indeed. So those, if I look at two supersymmetry preserving vacua, then there is a BPS domain wall, a domain wall that preserves some of the supersymmetry that sits exactly on this, which tells us that this Lagrangian, the supergravity Lagrangian, looking at these two particular supersymmetric minima, it tells us that there can't be tunneling between those two supersymmetric minima because it's right on the edge. Okay? Sorry? Exactly. Okay. Now, so on one side of this wall in potential space, the positive energy theorem prevents tunneling to negative cosmological constant. Negative cosmological constant, I told you, was a big crunch. Suppose I'm on the other side. Do I tunnel to a big crunch? And the answer is certainly not in the way that you're used to from ordinary quantum field theory. In quantum field theory, when I have a tunneling process like this, what happens is I tunnel here, I form a bubble of the so-called true vacuum, which we now know is really a big crunch. And that true vacuum bubble expands at the speed of light into the external space, and so any time-like observer is swept up in it. Is that what happens if I have an asymptotically flat solution of a theory of gravity, which has the same kind of tunneling instability? And the answer is no. And the reason that the answer is no is, again, because of black holes. So suppose at the moment that the bubble nucleates, someplace else, there was a black hole sitting in space. What happens? Well, bubble walls only expand asymptotically, at most at the speed of light. But the way black holes behave is that the space inside the black hole is receding away from the outside at a speed faster than light. That's why there's a horizon. One way of thinking about what's going on in a black hole classically, if you think in coordinates that are appropriate to talking simultaneously about the inside and the outside is that the black hole is black because the inside runs away and stretches out faster than the speed of light. You shoot light down into the black hole, and it can't get back out because there's too much space between it and you, and that space is growing faster than it can move. So that's why a black hole is black. It's also why black holes don't get swallowed by Coleman-de Luce bubbles. So in fact, the final state of a Coleman-de Luce tunneling from asymptotically flat space into space with a negative cosmological constant, big crunch, is the final state depends on the initial state. Depends how many black holes there were, or in fact, it could be that someplace far away from the bubble nucleation, there was some stuff that hadn't yet formed a black hole, but will form a black hole before the bubble reaches it. And that stuff also escapes, doesn't escape forever. It hits a rather different kind of crunch inside the black hole. But the generic picture is a space-time whose asymptotic future consists of a whole bunch of causally disconnected space-like singularities. What that could mean, I don't know. And I believe we'll never have to ask this question because of another thing that I believe in. And this is something where most string theorists I've talked to actually believe as well, namely that having lambda equals 0 is only possible if you have exact supersymmetry. And if you believe that, then you're always on the right side of the Great Divide, and there is no such thing as Coleman-de Luce tunneling. So I've now told you that for negative cosmological constant, Coleman-de Luce tunneling doesn't make sense. If I start from an ADS space, I should be more careful. Not any negative cosmological constant solution, but an ADS space. Tunneling, that space tunneling to some other state doesn't make sense. Why is it complaining that there's no power? Because it's not plugged in. Doesn't make sense. And if you believe that zero cosmological constant is correlated with supersymmetry, then it also doesn't make sense for zero cosmological constant. So this is not quite what everybody believes, that gravitation is just a small perturbation on the basic picture of tunneling in quantum field theory.
Basically, you dealt with classical gravity here. There was no high energy. When you're talking about possibility of
In the big
tunneling
crunch, you
down,
get arbitrarily high
yeah,
energy.
but the issue whether you can form instantaneous pulse-vacuum decay bubble, you basically use the classical.
That's right. So one of the big points of my lectures will be that the essential clues, because of the connection between black holes and high energy density of states, many of the essential clues to the fundamental behavior of quantum gravity at very high energy densities is actually stuff that we can learn about by doing classical gravity. And this is a precise example of that. So the idea that many of us had, including myself, that somehow the string theory formalism was going to change our understanding of the high energy behavior of gravity, that I think is wrong. That in fact, the high energy behavior of gravity always, always, always has to do with black holes. And if we want to understand fundamentally what theories of quantum gravity are about, we have to understand black holes. And perturbative string theory taught us an enormous number of things, but it was bad in the sense that it allowed us to evade this particular conclusion for a long, long time. And for most of us, it's allowed us to evade it up to the present minute. Okay. Now, what happens when you add a small positive cosmological constant? If you were originally, when I say add, what I mean is I take exactly the same potential with zero cosmological constant, but I just lift it up by a small constant. I add a small positive constant to the same formula. what happens? I now have, instead of a lambda equals 0 point, I have a minimum that has a de Sitter space solution. What I claim is, and this I hope to show you, is that if you started out on the positive energy side of the Great Divide, then the probability of tunneling goes like, in order of magnitude, the exponential of minus the area of the de Sitter horizon. That area was interpreted by Gibbons and Hawking as an entropy of de Sitter space, and ever since their paper, people have been trying to figure out what that entropy means. I'm going to interpret it as the logarithm of the number of states in the quantum theory of a stable de Sitter space. And if that's the case, we can understand this formula qualitatively very simply. Namely, if I have a system with a finite number of states, like the air in this room, it's a quantum system with a finite number of states, it has a finite probability to do really peculiar things, the most famous of which is all gathering into a 1 centimeter cube in that corner up there. Okay? That can happen if the system has a finite number of quantum states and you leave it undisturbed for a long enough time. If that happens, we don't say that the system has decayed into a disaster. What we say is it's a system with a finite number of states. There's a Heisenberg/Poincaré recurrence time. That means in a system with a finite number of states and a rather generic Hamiltonian, you will visit every state within a very small error. You'll visit every state if you give me enough time. And the amount of time, roughly, now it starts to depend on whether you're talking about Heisenberg recurrences or Poincaré recurrences, but the amount of time for Heisenberg recurrence is e to the minus the entropy. And this is something we can understand from Fermi's golden rule. What we're saying is that there's some transition from a typical state in this room to the state where all the air is up in the corner. That transition, by quantum mechanics, by unitarity, that transition also goes backwards. Okay? But if I'm thinking about what the probability is to see that transition, it's a lot smaller if I'm in a typical state that the system likes to be in most of the time. A typical macroscopic state will not look like that state down there. It looks like it 1 over e to the entropy of the time. And that's a rough estimate without even calculating the matrix element for the transition. That's a rough estimate of the transition probability. We'll see that the formula for de Sitter tunneling is not exactly e to the minus the area. And I would interpret that extra factor as the transition probability as in the square of the matrix element. And this e to the minus a factor is just Fermi's golden rule. And there is evidence in the actual formulas for Coleman-de Lucia tunneling from de Sitter minimum to another de Sitter minimum that this interpretation is correct. Okay. What is that evidence? The de Sitter instanton is very, very different from instantons for the putative decay of flat or negative cosmological constant space. The de Sitter instanton is a compact Euclidean manifold. The simplest way to understand that is when you talk about instantons in general, you insist that the instanton approach the false vacuum asymptotically at infinity. That's the definition of the instanton. It describes the creation of a bubble of true vacuum inside the false vacuum. So you take the Euclidean version of the theory, you look for a field configuration that approaches the vacuum state you want at infinity. And in the anti-de Sitter space, you have to be really careful about how fast it approaches, because sometimes you're not actually talking about a state, as Horowitz and Hertog taught us. But in de Sitter space, well, you know what de Sitter space looks like. It looks like a time-like hyperboloid, a sphere rushing in from infinite radius at infinity, coming down to some finite radius, and then rushing back out to infinite radius. That's a very symmetric space. What happens when I analytically continue it to Euclidean space? I have to get a Euclidean manifold with the same symmetry group. And the symmetry group here is SO1 comma P in Minkowski space. So when I analytically continue, I get a manifold whose symmetry group is the full rotation group. And there's one such manifold. It's called the sphere. So those of you who didn't know this already, Euclidean de Sitter space is a sphere. All right? It's a positive curvature sphere, that positivity having to do with the positivity of the cosmological constant. Euclidean anti-de Sitter space is a hyperbolic space. You change the sign of the curvature. It's like going from the Lobachevsky plane to the sphere. So what do I mean by the instanton has to approach the vacuum at infinity? Well, it can't, because there ain't no infinity in the Euclidean vacuum state of our theory. It's a sphere. Well, it turns out that, like the sphere, the instanton is a compact Euclidean manifold. It just looks a little bit non-spherical. It looks like an egg. It's an ovoid. That compact Euclidean manifold, like the sphere, has a negative action. So that's kind of funny, negative action. Well, Euclidean gravity does have this problem, that the action can become arbitrarily negative. Okay. The action of de Sitter space is also negative. The action of de Sitter space, now this means action, not entropy, even though I use the same letter for entropy. Action of de Sitter space is minus the area in Planck units. So it's minus 1/4 the area in Planck units, minus pi r in Planck squared in 4 dimensions. The action is negative. The entropy is positive. All of that makes sense. How can a negative action instanton make any sense? What's the probability in terms of that action? The probability you get by evaluating the path integral. It looks like it's e to the action. Well, not true. If you go back to the very beginnings of your quantum mechanics course on instantons, you learn that you have to subtract out the action of the place you started from. Okay? And so what I should really be looking at is e to the minus s instanton minus s de Sitter. Okay? And this thing always turns out to be positive. The de Sitter action is more negative than the instanton action, so that this quantity turns out positive and has the definition of a probability. But now something really interesting happens in the case where I have 2 de Sitter minima. Because now I can form 2 different formulas like this. I can form e to the minus s instanton minus s de Sitter 1, and I can form e to the minus s instanton minus s de Sitter 2. And these things, roughly speaking, correspond to instantons tunneling from 1 to 2 or from 2 to 1. And in de Sitter space, both of those, from de Sitter to de Sitter, both of those transitions are possible. One way to think of that heuristically is de Sitter space is a space with a finite temperature. And so if you have a finite temperature, even if you're in the more stable of 2 states, there's some probability of thermal fluctuation into the other one. We were just talking about that when we talked about air collecting up in the corner of the room. And in fact, this gives you exactly that formula, because if I take the ratio of these 2 transition probabilities, I'm going to get this wrong, I'm sure. If I take P12 divided by P21, I get e to the minus the difference in the entropies. Now, that's a formula some of you might be familiar with or almost familiar with from statistical mechanics. There's something called the principle of detailed balance, which says that when you have two states in thermal equilibrium, when you go back and forth from one to the other, essentially for the reason that I said, because the matrix element of the evolution operator is just conjugate for the backward transition, the probability of transitions differ by the exponential of the number of states. Now, in thermal equilibrium, you usually get the exponential not of the entropy, but of the free energy. This formula, which is the exponential of the difference of the entropies rather than the free energies, is appropriate for a system that's at infinite temperature. Okay? And in my last lecture, when I start to talk about the quantum theory of de Sitter space, I want you to remember that fact. All right? Yeah?
So one of those two formulas, you can derive, suppose, to the extent that you can do any Euclidean path integral derivation, by doing the Coleman-de Lucia derivation.
Yes.
The one where you decay from 2 to 1, the only way I'm aware of to derive that formula is to start from detailed balance and then go the other way?
No.
So you say there's some path integral
Sure.
derivation of there's a geometry that describes.
Yeah, if you look at the instanton, it's the same instanton. It's the same geometry. This SI in the formula is the same for the two cases. What that is telling you is precisely that the matrix element for these two transitions is the same. And that the probabilities are differing only by the exponent.
Lorentzian geometry you can sew onto, which somehow describes the whole space fluctuating up into. It seems like it's a more quantum thing because the finite temperature of de Sitter is a quantum thing.
Okay, I don't know the answer to the question you just asked. I'll think about that. Okay. Temperature infinite for a system with a finite number of states is the very simple statement that you've just picked a random state in the ensemble of all possible states. That's what it means. The thermal ensemble at infinite temperature is just the maximally uncertain density matrix. And if you've only got a finite number of states, that's a perfectly sensible quantum density matrix.
Or the Hamiltonian is 0?
Sorry?
Or the Hamiltonian is 0.
Yeah, that's not a good, that's a bad thing because when what's happening is you've got a chaotic Hamiltonian which mixes the states, and you start with a random initial state, you generate the infinite temperature ensemble. If I start with a Hamiltonian 0 and I sit in any particular state, I'll never move away from it. So the idea that the de Sitter is thermalized depends rather on the idea that it's at infinite temperature with a random Hamiltonian. Okay. And that will be important in my discussion of de Sitter space. Now finally, how much time do I have left? Sorry? 5 minutes. Oh, that's really bad. Okay. So some of the details I wanted to show you, I will only show you next time. I'm also making them one of the homework assignments. And I hope to have those notes to you, still very incomplete, by tomorrow. And so you'll get to do that homework assignment. But it's essentially proving all of these statements. Let me quickly talk about the transitions between de Sitter space and zero cosmological constant. And I'll think about that in a simple situation where the zero cosmological constant minimum is isolated. Okay? The one that is more likely to be relevant for any discussion of the string landscape is the case where the potential actually asymptotes to 0 out at infinity, and you have to think about solutions that don't actually come to a a stable stop, but just go running out to infinity in field space. Nonetheless, one thing that follows from these formulas is that in this limit, the reverse transition from the zero cosmological constant situation to the finite cosmological constant situation goes to zero. The probability of that goes to zero. And so that suggests, given my hypothetical interpretation of these facts, that that system that we get in the limit, if it really corresponds to a real theory, is a system that has an infinite number of quantum states. Now that makes sense for somebody who thinks of this as asymptotically flat space. But the space-time that you get at the end of Coleman-DeLucia tunneling to zero cosmological constant is very much not an asymptotically flat space. It's a space-time that has a null future infinity, just like asymptotically flat space. But it has energy densities which are constant on negatively curved space-like hypersurfaces. I drew that incorrectly. Yeah, I'm sorry. I drew that backwards. The surfaces look like this. An asymptote to this light cone. And so if I set up here and try to define an asymptotically Minkowskian coordinate system at infinity, I fail, because I always run into these regions of ever and ever larger energy density from the past when I go far enough away. So this system is not asymptotically flat space. It's different. What it is, I don't know. These formulas seem to suggest it has an infinite number of states. I will later tell you about an argument that seems to suggest the contrary, and I don't really know whether this process makes sense or not. This process of tunneling from a positive cosmological constant de Sitter space to a situation with zero cosmological constant, perhaps only asymptotically in field space, is the crucial question that one has to answer if one wants to make sense of the conventional string theory landscape interpretation of de Sitter vacuum states. I will be pursuing another path entirely in which I'll concentrate on this picture of stable de Sitter space with no tunneling to asymptotically zero cosmological constant. As I told you, I can tunnel to negative cosmological constant big crunches, but those should not be thought of as decays, but rather analogous to the air bunching up in the corner of the room. And with that, I'll finish for today.